In our last lecture, we talked about the framework is rigid. We know the framework contains a graph and a realization P. In this lecture, we would like to associate the framework with some motions. Suppose other agent, they are described, the dynamics are described by the single integrator dynamics. Let's say we can directly control the speed of every agent instantaneously. Also, let's put agent exactly at their initial realization. For the initial position of agent at their realization, then we know the distance constraint are satisfied. Okay? The distance between xi, j is same with dij. What do we call a flex or reconfiguration? Is now we want the agent to move. So the motion of the continuous trajectory, we have xt. So if the trajectory can make the distance constraint satisfied for every t, then we call such motion is flex or reconfiguration. You can think of it in this way. We may have many different realizations. If we can find one realization, then we can find many realizations. But pay attention here, we require non-trivial rigid motion. So the one with translational motion and rotational motion does not count. Now let's give another definition called infinitesimal motion. For infinitesimal motion, not only we put agent at the initial realization pi, but we also require the initial velocity vector must be satisfied the difference between, for every edge, the velocity difference between uj and ui is orthogonal to the difference of the state vj and vi. So here is in the product, basically it says, if we write in the vector form, it's uj 0 minus ui 0 transpose times xj 0 minus xi 0 is 0. So we call a framework is infinitesimal rigid if the only infinitesimal motions, that's the one satisfy these constraints, are trivial. Basically means infinitesimal translation or rotational. Okay, the only one can make this constraint satisfied are translational motion or rotational motion. Then we say this framework is infinitesimally rigid. If a framework is infinitesimally rigid, basically means the graph is rigid. It's easy to understand. If the only, you can think of the only motion, okay, are translational motion and rotational motion. Of course, the framework is rigid, but the opposite statement may not always true. Even if the graph, the framework is rigid, that means the framework is infinitesimal rigid. Let me give you some examples. Okay? Before I give you some example about the difference between infinitesimal rigid and rigid, now let's look at some trajectories, what we call about continuous motions. Now we have a framework. We know a framework contains a graph G. Graph G, it has the vertex set. Here we have agent 1, 2, 3, 4. Then we have edge set. We have 4 edges. Then we define the distance constraint. Suppose the distance between agent 1 and agent 2 is 1. The distance between 1 and 4 is 1. Distance between 2 and 3 is 1. And distance between 3 and 4 is 1. Then we can find one realization P. Let's say we pick 0, 0. The position of agent 1, 0, 0. So position of agent 2 as 0, 1. Agent 3 as 1 and 1. And agent 4 as 1 and 0. Now let's see the definition of flex or reconfiguration. If we can find some input UIT to make the state constraint satisfied, but the motion is not translational motion or rotational motion, and also can keep distance constraint satisfied. So what we can do, we can put U1 at 0. So agent 1 stay where it is. We put agent 4 at 0. Then we can give the same, let's say U2 is 1, is 1, 0, now it's 0, 0, and U3 is 1 and 0. Okay? Because maybe we need to put, let's say, in this way. Okay, put a little bit in here, yeah. So we can pick, let's say, U3 as 1 and -1, 1 and -1. Basically, we want to keep the distance as the same. So it will be, let's draw a circle. Okay, this will be this figure. Okay, then distance constraint is satisfied. Then we can define a flex or reconfiguration. So if you're unclear what I got this configuration, you can, let's say, draw a quarter circle, then agent 2, agent 2 travel on this arc, agent 3 travel on this arc. So distance is still 1. Then we define another motion. Array configuration. Now let me give you the example about infinitesimal motion, infinitesimal rigid, and rigid. Okay. Now we know for this graph, it's a rigid graph. We have agent 1 and agent 2. You have to remember that infinitesimal motion, it cannot keep the distance. Yeah, infinitesimal motion may change the distance between agent 1 and agent 2. Yeah, let me give you the example. This is the definition of infinitesimal motion. It only needs to satisfy the initial velocity, the difference of initial velocity times the initial difference of the position is 0. So infinitesimal motion may change the distance between two agents. Now we have a framework, G. Then we have vertex side V. We know what is V, V1, V2. At site only one element. To D, let's say we don't need to specify the distance, okay? Let's suppose we have realization P, agent 1 as 0, 0. We pick this one 0, 0. If we pick agent 2 as 2, 1. Now we know the difference. X1 minus X2 will be -2 and -1. Then we can pick U1. We can pick U1 as, let's say, 0.5 and 1. We can pick U2 as 1.5 and then -1. Then we have U1 minus U2 will be -1. Then we have 2. Now we use U1 minus U2 transpose times X1 minus X2. Then we have -1, 2 times -2, -1. Then we have 2 minus 2 will be 0. Okay. So in this, if we pick this initial velocity, so it may change the length between agent 1 and agent 2. So in other words, infinitesimal motion does not keep the distance as constant. Now, what do we mean? Now we can say that we can give another definition. So based on the result and the velocity difference times the position difference is 0. So if this condition is satisfied for every edge, then we know this motion is infinitesimal motion. Then actually we can pick it in a matrix form by this R matrix. It includes both the graph and configuration and the velocity vector. Then we call the matrix R is rigidity matrix. So the rigidity matrix has the row. The row will be the number of edges. So the column will be M times P. So the P will be the dimension of the vector. Then M, it should be the number of agent. Okay. So in this way, let's say in the S row, the ij row, for let's say some k row, we have the edge ij. So on the other hand, we have u1, u2, then we have, let's say we have um. So for each ui, it belongs to rp. Then we know for this one is pi, pj transpose. Then it will be a row vector. The size of the row vector will be rp. Then it times ui, then plus upj minus pi transpose times uj is 0. Then if we change it to pi minus pj, so we put a minus sign here, then we get the same result. Okay, the pi minus pj transpose ui minus uj is 0. Then we have this rigidity matrix. Then we have another motion, another definition of the infinitesimal rigid. If this matrix R, rigidity matrix times U is 0 for all infinitesimal motion U, then this framework, graph and configuration is infinitesimally rigid. Then let's discuss the problem. Let's say M is 2. Let's discuss it's in planar graph. Let's say we have the number of agents is greater than 2. Then the framework is infinitesimally rigid if and only if the rank of the rigidity matrix is 2n minus 3. So here N is the number of agent. Then we know the framework is defined for a graph and a realization. Now we want a concept that is defined only for graphs, independent of the realization. So this is called generically rigid. If we have graph, have vertex set V, S, E, and distance constraints, it's generically rigid if it has an infinitesimally rigid realization. Okay? Basically means the realization, the infinitesimal realization is only infinitesimal translation or infinitesimal rotation. If we can find such realization, then we know the graph is generically rigid. So generic rigidity is a property of the graph, okay, not the framework. So if a graph is a rigid graph, basically we mean generically rigid. So later on, we just use the two concepts interchangeable. Whenever we mean a graph is a rigid graph, it means the graph is generically rigid. So a graph and a realization is infinitesimally rigid. Then we call this graph a rigid graph. Then we call the P is generic configuration for the graph G, and GP is a framework, it's generic realization. So if the graph G is generically rigid graph, then the set of all generic configuration, this means all set of P for graph G is a dense open subset in the subspace of R M times N. So here N is a number of agent. So M maybe 2 if it's planar space. Or 3 in 3-dimensional space. Now let me give you some definition about what is dense, what is open subset. This is from the book Principles of Mathematical Analysis. Let X be any metric space, then a point P is called a limit point. So let me draw you something. Let's draw an open circle. Okay, let's pick a P on the boundary. Then the P is a limit point if every neighborhood of P, let's say this is the E, contains some point Q. So the Q, okay. No, that's not, that's not. Okay. Let's say if, let's draw a set E. If P is a limit point, then every neighborhood of P contains a point Q, and Q also belongs to E. Okay, if a P belongs to E, basically there's many points very close Q, very close P also belongs to E. So this P is a limited point. So if P is interior point, okay, some here, then it means for every neighborhood of P, we have N, and N also belongs to E. So if E is an open site, then every point of E is an interior point of E. Then for every E, we can find a neighborhood. Okay, it belongs to E. Then what means dense? Means every point. Okay, every point is either a limited point or a point in E. If not a point in E, it's a limited point. Now, lastly, like talk about the minimal rigidity. So a graph is minimally rigid if it is rigid, but it is not rigid if we remove a single edge. So how do we say a graph is minimal rigid? So if and only if this applies in planar space, it has 2n minus 3 edges, and also each induced subgraph. If you still remember what induced subgraph basically means, if you remove some vertices, you also need to remove the associated edges. So if for every each induced subgraph, if you want to keep q vertices, then the induced subgraph has no more than 2p minus 3 edges. So then the graph is minimally rigid graph. So why we would like to introduce the graph rigidity? So suppose the formation are both translational and rotational invariant. Then the shape can be specified by using the inner agent distance. If you can design some algorithm to make the interagent distance constant, then the graph will not change the shape. The shape will be kept all the time.